Uh, Hello? Oh, yes. Too much, perhaps. I'm going to start again. I'm Donna McCormick. I'm the Executive Director of Montauk Observatory. We're co-sponsoring the lecture tonight with the East Hampton Library, and we're very grateful to them for serving as our co-sponsors, especially Dennis, who was wonderful in terms of helping coordinate this, and Rick Gilbert, who is a board member at the library. How many of you have heard about Montauk Observatory before? Oh, good, but at least half of you haven't, so I'm going to tell you about it. We were founded in 2005 for the purpose of fostering interest in science education, particularly astronomy, on the South Fork of Long Island. To that end, we've established the first astronomical observatory on the South Fork. It's located on the campus of the Ross School, right next to the tennis center. And eventually we intend to have that online, accessible via the internet, so students and teachers and researchers and you guys can log in and use the telescope, which is one of the biggest on Long Island, actually. It's a 20-inch accretion design. Can do some astrophotography or just explore your universe. And we also hold lectures like this one at various nonprofits across the South Fork. All of our events are held free of charge. We don't want to discriminate on the basis of economics, but as a result, we operate on public donations, small little gifts from those who appreciate our efforts. And if anybody's interested, go to our website and make a little donation. Well, I think that's all I have to say about the past of Montauk Observatory. In the future, on August 3rd, it's a Saturday, and it's going to be at 2 o'clock in the afternoon at the Ross School. We have Carter Emmert speaking. He is the Director of Astrovisualization at the American Museum of Natural History. He's the guy who did all those amazing IMAX films for the Hayden Planetarium. So he's going to be talking a little bit about the moon, some visualization techniques they've utilized to see where research has been done on the moon, but he's also going to spend a good deal of time talking about the possibility of using the moon as an international base to further explore the rest of the galaxy, especially Mars. So hopefully you'll all come to that. There's information about that on the flyer in the back. Also have some sign-up sheets if you want to join our email list for event notices. I promise I don't abuse that. Maybe once every couple of weeks you'll get a little something from me. And I guess that's it. What I would like to do right now is introduce Rick Gilbert, who, as I said, is a member of the East Hampton Library. Rick himself is on the board of the library, but he himself is interested in astronomy. He was on the board of the Antique Telescope Society for many years, and he's also a co-founder of the SSRO, Star Shadows Remote Observatory at observatories at New Mexico Skies Observatories and Cerro Tololo Inter-American Observatory in Chile. We're hoping to have him do a talk sometime soon. So I'm going to give Rick over, and he will tell you about Paul Steinhardt. And thank you so much, Paul, for coming here tonight.
Thank you. I'm actually excited to do this introduction. I'm sorry, can you hear me okay? I'm very excited to do this introduction. Paul is a pretty famous guy. The last time I had anything to do with a famous physicist was when Hans Bethe let me carry his briefcase a few feet. I am Rick Gilbert. I'm the chairman of the technology committee at the library board. And I have a distinct pleasure in introducing our speaker tonight, Paul J. Steinhardt. Paul is the Albert Einstein Professor of Science at Princeton University, where he is on the faculty of both departments of physics and astrophysical sciences. It's unusual in the fact that his work spans many disciplines, ranging from the origin of the universe to new forms of matter. He's received many honors, including the prestigious ICTP Dirac Medal, and is a member of the National Academy of Sciences. Paul is the author of The Endless Universe Beyond the Big Bang, which I think came out in around 2007 or so, and most recently the co-author of The Second Kind of Impossible, which is really a wonderful new book about his search for the naturally formed quasi-crystals, and I'm sure he's going to tell us lots about that. Let's welcome Paul J. Steinhardt.
Well, thanks. Thanks, Rick, and thanks, Donna, for having me, and thanks, Cheryl, for working behind the scenes to arrange things to make this evening possible. So, so what I'm going to tell you about tonight is a brief excerpt or a brief snippet or a brief snapshot from this book that Rick mentioned, The Second Kind of Impossible. It's at one level a science story. So, and being a science story, it's meant to be a true story. Okay, to the best of my knowledge, everything in this book is true, although you might not believe it at various times during the story, because it has many other aspects to it. It includes a true life adventure story to a remote part of the planet. It includes a first-class international detective story. There are villains, there are heroes, real villains, real heroes. There's a father-son story somewhere in the middle of that. There's a man of many miracles I'll introduce you to. Stunning architecture and remarkable mosaic patterns if you're interested in art and novel patterns, things that very few humans have seen before. And there's a futuristic space odyssey. So depending on your taste, as you wait a few pages, the subject will change and go into a new direction, and it's all part of one overall story. And it's a story that also includes many interesting characters, some of whom you know, some of whom you don't know. Here's a fellow you probably have not heard of. He's not a very well-educated person. He was a French priest, rather clumsy fellow, so clumsy that he had an accident, and as a result of that accident, he made one of the most important discoveries in the history of science. So important that his name is emblazoned on the Eiffel Tower as one of the great Frenchmen of the time that the Eiffel Tower was built, but you probably never heard of him. You may have heard of this fellow. His name is Richard Feynman. He was a mentor of mine when I was at Caltech, and he plays a small role in this story as well. Most importantly, an important inspiration to me. But there are other famous physicists, scientists in the story. Linus Pauling is another example. There's Nobilis. There's, have heard of. A fellow whom you may or may not heard of. He's a very important geologist at Princeton University. His name is Lincoln Hollister. I know that the Montauk Astronomical Society just recently celebrated Apollo 11, the landing of the first men on the moon. Well, one of the important things that happened in Apollo 11 was the first time that humans were able to collect rocks from the moon and bring them back to the Earth. And those precious samples went to a few people, including this fellow. And so he recipient of the first moon rocks taken from the moon, which has almost nothing to do with the story I'll tell you tonight, other than to qualify him as a well-known geologist. Then there are probably people you've never heard of, like this fellow. He is, you might call him a mining geologist. Others might call him a prospector who works in Far Eastern Russia. And then the story also includes creatures, creatures great, creatures small. Everybody plays a role in this story at one time. So it's pretty hard to summarize in an hour, what goes on in the story, but I'll try to give you a taste of different aspects of the story, beginning with the pure science. So what is the story is most about is in the title, the second part of impossible. Impossible is the first word in chapter 1. It's the last word in the last chapter, and I forget how many times it appears inside the book. The word impossible and trying to accomplish impossible things occurs and reoccurs throughout the story. Constantly, there are times when it looks like things are hopeless and something happens miraculous, or sometimes with a little intelligence and saves the day and keeps the story going. But more generally, one of my motivations for writing this book was to bring up the issue, generally, what does a scientist do when faced with something that's said to be impossible? Sometimes you have an idea, you bring it to an expert, and they tell you that's impossible. And most people, that's enough to make you go running the other direction and forget that you ever asked the question. Um, Even more so if it's not just one person saying it, but if people have been saying the same thing for hundreds of years, that it's impossible, you tend to think that doing. But as a real scientist, as a true scientist who's working in the field, let me tell you, that's actually not the right reaction. The right reaction is to ask yourself a question, which is, as I like to put it, what kind of impossible do you mean? Do you mean the kind of impossible like, is 1 + 1 = 3? Is it something that's truly impossible, something proven to be impossible, that incontrovertible argument, it can't be done? Or is it, like often happens when someone says something impossible, the second kind of impossible, where based on what we thought we've known and based on certain assumptions, sometimes you don't even know what those assumptions are, they're unstated, it's declared to be impossible. But if you can figure out, if you can trace back to find out what those assumptions were, and if you can figure out a loophole, that's a great way of discovering something really exciting, because not only will you discover something new, but you'll discover something new that everyone thought was impossible, which is the most exciting kind of discovery. So let me try to give you a clue of what I mean by these different kinds of impossible by giving a simple example. Suppose you were sent a bunch of tiles and you're asked to tile your shower floor. Suppose they're square tiles. You want to know, can I tile my shower floor without having any space or gaps in there? Is that possible? Well, of course, it's possible. Many of you may even have such showers in your home, tiled in this way. But this simple picture is enough to illustrate the point that this is certainly possible. Suppose instead you were shipped a bunch of tiles which were a different shape. Suppose they were in the shape of a regular pentagon. Okay, you again go to try to tile your shower, and whoops, it doesn't look very good. There's all these gaps in there that are in that. Now, question, is it impossible to tile the floor with pentagons? Or is it that you're just not being clever enough to answer the question? So this is an example where we actually know the answer to the question. It was proven about 200 years ago. It's actually related a little bit to that I was mentioning. And we know this is, absolutely impossible. Impossible of the first kind, that is to say, as impossible as 1 + 1 = 3. So no matter how you put together your pentagon tiles, you can't do it. In fact, there's only certain shapes you can use to tile. If you're using a single shape, there's only certain shapes you can use, and they correspond to rectangles or squares. You can't use pentagons. You can't use heptagons. You can't use octagons unless you also put in little squares, but that's effectively making a square pattern. You can't use any other shapes. There's an infinite number of shapes which are impossible, and a finite number, a handful, which are possible mathematically. Now we can ask the same question in 3 dimensions. Instead of using tiles, I now want to use building blocks. So suppose I have cubic blocks. Can I fill space? Can I fill this room with cubes without leaving spaces? Well, I think all of you solved that problem as children, as toddlers. Of course you can. That's what building blocks are all about. You can stack them up and you can make that's possible. But suppose I gave you a different shape. Suppose I gave you this shape. So this shape, and I'll pass around. Happens to be in the form of a dungeon. Study the shape when it comes by. You'll see enough to figure out how to get them to fit together? Or is that something which is known mathematically, rigorously, to be impossible of the first kind? Well, it turns out this is known to be impossible, and it's impossible of the first kind. Again, proven back about 200 years ago. Now, why should you care about such things? Why is this? Well, it's not just important mathematically. It's important because it tells you something about what forms matter can take. Matter is made of atoms. Atoms join together to make a solid. So putting together building blocks or putting together. And in particular, one of the shapes they like to form when you have a small group of atoms is this shape, the shape of the icosahedron. That turns out to be a very low energy shape that atoms like to form when they're few in number. On the other hand, if I could start to put a lot of atoms together to make a solid, to make a form of matter that I might use for some application. One of the first things that one learned now know it exists. So something has happened that's allowed us to get around this impossible rule. That's changed the impossible of the first kind to the impossible of the second kind. And not only is it possible in principle, but there it is. There's an example of it. The idea, their explanation for how this is discovered accidentally in the laboratory. Accidentally made it. Meantime, there was a group of us, absolute no-no from a U.S. geologist's point of view, is he sliced and diced the material, losing most of the material right off the bat by doing that. But then he could study the individual slices using something called an electron microprobe. And what a microprobe allows you to do is wherever you touch down, it tells you what the local chemistry is. How much copper, how much aluminum, how much iron, things like that. So every one of these spots, numbered spots, is one of the tests that he did in this slice. And all the yellow ones there turned out to be copper aluminum 2, which is exactly the chemical formula for Katirkite, which is exactly what the box said was in the box, which might seem to you like something trivial, but you'll see in a bit that wasn't trivial. That was a huge stroke of luck. That wasn't an obvious outcome. But then that wasn't all that was in the slice. The red things are all another chemical composition. Again, copper, aluminum, but now a one-to-one composition. That's another known mineral, it turns out. Crystallographers know it. It's called cupellite. It's registered. It's known. So those two were known things. Then there were the green ones and the blue ones, and those didn't correspond to anything with the right chemistry that was known among crystals. So those were the targets to go for. And then it turned out the green one turned out not to be interesting, and the blue one looked promising. Okay, so now Luca committed the next cardinal sin, which is he tried to poke out the little blue ones from everything else, in the process destroying the rest of the sample. So what that meant was, by the time he poked that out and sent it to Princeton, the rock was essentially gone. And there were just little specks of material. So when I finally got to Princeton and I looked in the box, I could barely make out anything. I thought, this is ridiculous. If this turns out to be the real thing, I was hoping to at least, it was something fit in my hand, not something I can barely make out with my eyes. But I had to deal with these little specks, which were, microns or fractions of microns. That's a millionth of a meter, smaller than a human hair. And so we took out one of these little powdery grains and when we looked at it, we're like in that, where that red circle is, it was thin enough for the electrons to pass through it. And when we looked at it, voila, bam. Fantastic quasi-crystal pattern. This is heavily overexposed. That's why it looks so cruddy, but it's historic. It's actually the first sighting of a first natural quasi-crystal ever, first quasi-crystal ever found in nature. And what's really cool about it is that that sample, samples we found that were perfect in the perfect in the laboratory, they're made under highly controlled conditions. Our sample is not made under highly controlled conditions. We went to measure the composition of it, we found something really amazing. It was 63% aluminum, 24% copper, and 13% iron. Well, the reason why you should care is that composition was a known composition. That is the composition of the sample bona fide quasi-crystal. So it turns out nature has managed to make a quasi-crystal, not the way the Japanese made it under highly controlled conditions, but in this complete mishmash of rock. What does nature know that we don't? How does it know to make a quasi-crystal? Complicated mess, which you'd never, ever in the laboratory attempt to do. That led to the question, which asked me, not to ask a material scientist, but to ask a geologist. What does the Earth know, or what does the nature know that we don't know? What can you tell us? And that's what led me to walk to the office of Lincoln Hollister up the street, tell him the story I've just told you, and ask him, what does this tell us about nature, or what is nature telling us about quasi-crystals? After hearing the little story, that gave me this book. We now since learned it's called the Hollister Gaze, which means beware, something bad's going to happen. And he said, well, I'm sorry to tell you, but what you have there is impossible. You mean impossible? I said, no, these quasi-crystals exist in the laboratory. We've made them. Okay, we know they're possible. He said, oh, no, I don't know anything about quasi-crystals. That's not what bothers me about your story. What bothers me about your story is that your material, you said, has aluminum, copper, iron, all in metal form. That's an impossible thing to happen in nature. Nature hates to make metallic aluminum. Plenty of aluminum in the earth. It's the third most common element in the earth. Anyone that has a sapphire or ruby is carrying an oxide of aluminum. You may not think about it that way, but that's what you're carrying. Okay. So aluminum is very common, but it loves oxygen. It never wants to be without oxygen. It takes a lot of energy to separate aluminum from oxygen. That's what aluminum foundries are all about, is using the energy of a hydroelectric dam to separate aluminum out. So he said, surely what you've got there is a piece of slag, some sort of byproduct of. And that's when I stopped to ask him the question I told you at the very beginning. And I actually said it out loud. I said, did you mean the first kind of impossible? The second kind of impossible, that based on experience you haven't seen it before, but doesn't really violate any fundamental laws of nature. And unfortunately, he did not throw me out of his office, but he actually stopped and thought for a moment. He said, okay, I can imagine one circumstance, it's pretty extreme, but in which you could form such a material deep under the surface of the Earth. I mean, really deep, thousands of miles deep, near the core mantle boundary. Those conditions of high pressure are enough that you can separate aluminum from oxygen. Of course, then you have to figure out how you found it on the surface of the Earth. And he said, but, you know, there's a famous theoretical geologist in my department who claims that at one time the Earth had super plumes that could carry material all the way up from the core of the Earth to its surface. And that theory has never been proven. And I thought, okay. So it's not impossible of the first kind. It's impossible of the second kind. Very unlikely to be true, but if true, really, really interesting. So that's game on. So, and then I said to him, well, because I had been thinking about this separately, I said to him, well, how about meteorites? there's no oxygen in space. And if we want to keep the oxygen away from aluminum, how about meteorites? And fortunately, he didn't know that that was a really stupid remark on my part. There's plenty of oxygen in space. Meteorites are full of oxygen. I didn't know it, and fortunately, he didn't know it. So he said, okay, well, look, I don't know anything about meteorites, but I do know a meteorite expert. He's at the Smithsonian. Let's go down next week and talk to him. And so Pearson, who also became a member of our team, he was head of the Division of Meteorites at the Smithsonian at the time. And when we got to the Smithsonian a week later, waiting at the door of the Smithsonian, out on Constitution Avenue, before we could even enter, was Glenn McPherson, who wanted me to know, me especially to know, before we even started the discussion. I want to let you know one thing right off the bat, that what you've got there is impossible, okay? He said, I know every kind of meteorite of every kind. I study them. I know everything about them. And no one has ever seen metallic aluminum in a meteorite. Definitely got there as impossible. And then we spent the next few hours walking through this Smithsonian to his office, in his office, on the way back from his office, and is talking continuously and telling me all the reasons why this was impossible. So by the time we left, you know, he was convinced it was some form of slag and that he would never see us again. Now, fortunately, or us, Luke and I, were both nutty enough and fanatic enough that we weren't about to take no for an answer, at least not just based on these kinds of experiential arguments. So we decided we would we would not give up. We'd try to figure out how this thing formed. And that broke the project up into two subjects, two major questions. Number one was a kind of detective story. According to this box, this sample came from a particular place in Russia. That particular place in Russia is nowhere near an aluminum foundry. It's in the middle of nowhere. So did it really come from there? And then the other thing was, we had a few little grains of material left. Could we study those grains and prove whether or not our material was made in nature or not? So that's what occupied us for the next 2 years. And almost every day, there was something happening or some things happening in each of these two stories. They were completely intertwined. And so some days would be good days, and some days would be bad days, and some days good days. And this is why Luke and I were talking every day and continue. So I can't tell you the story as in that form. I'm just going to focus on the one that's the kind of unusual story, which is the detective story, just to give you an impression of what that was like. So does the sample really come from the Koryax? What would you do? How would you answer that question? The rock doesn't tell you, okay? So it's in a box, there's a label on it. Should you believe the box? Well, by this time I knew that a lot of labels on boxes in mineral museums are inaccurate. There's a lot of fakery and a lot of mistakes. You can't trust the box. So what else could you do? You could ask, how did that box come to the museum? So we looked in the records and the archives, and we found that it had come to the museum. It had been sold by a fellow who lived in Amsterdam, gave the name of the person, didn't give the address of the person, and it had been sold in 1990, along with the other thousands of minerals that were in that set of drawers. So, okay, this is the day of the internet. You can get on the internet, and you can start to search for this guy. Does he exist? You can even speak Dutch if you're willing to use Google Translate and, you know, talk to people and ask them questions. And we spent several weeks doing that, and we didn't find him. I found someone that seemed to have the same name. He seemed to have disappeared in the mid-90s, but that's as close as we got to it. So that killed that. Next thing you can do. Next thing you can do is you can send an all points out bulletin out to every museum and every collector in the world with the internet, because they have different websites that they use, and say, does anyone else have this Katirkite? And, you know, can we borrow your sample and use it and test it? And after weeks of that, we've got five groups, five answers, of 4 in the West, 1 in Russia, that said, yes, we have that sample. And the 4 in the West were willing to send us the sample. And so we got those samples. They were able to remove a small amount of material of them and test them. And what we found was they were all fakes. Every single one of them. They didn't have aluminum at all or copper in them at all. They were fakes. So maybe this is an important thing to tell any of you who might be potential mineral collectors. You know, when it comes to art, valuable art, if you're going to buy a valuable piece of art, you have it verified. right? You have it tested for its accuracy, and you get a seal of approval. That's because art's very expensive, okay? But minerals are not expensive. It costs more to test them than it does for the mineral itself in many cases. So people buy the minerals. Collectors buy them because if someone says they have Katirkite and they read that's a new mineral, they want to have a sample in their collection. And maybe it is Katirkite, maybe it isn't, but now it's in their collection. Then someday, years later, they give their collection to somebody, to a museum someplace, and now it's in the museum's collection. The museum people also don't test it. They don't have, they don't have enough effort to test it. And sure enough, it's now sitting in your museum with that same name until someone comes along, like me, and offers to test your material. And that's actually why they agree to do it, because you're actually going to pay the bill, for doing the testing. And if you verify the material, that's great. If you don't, okay, it's another mineral that turned out to be a fake. Well, these all turned out to be fakes. But the one in Russia couldn't be a fake because that was that was what's called the holotype sample, the sample that first got these minerals declared to be natural crystals, the first discovery of them. When you discover a new mineral, what you do is you submit to the International Mineralogical Association your discovery, a description of your mineral, its properties. There's a team of 30-plus mineralogists from around the world who vote whether your data is good enough. If it's good enough, it gets voted in as an accepted mineral. And if it gets voted in, the next thing is you have to publish your data, and you have to put a sample of it in some public museum. So this sample in St. Petersburg was the result of that process. And so, okay, that's good. So we know it's bona fide. On the other hand, precisely because it's the holotype sample, you can't touch it. It's supposed to be pristine and not touched. Okay, so that's just the tradition. So that's no good. So we had to know, maybe we could track and find the people who had found that sample. Maybe they could give us more samples. And we knew who the authors were on the paper that reported it, and the lead author on that was a fellow by the name of Leonid Razin. So we began to track Leonid Razin. Come from? Where is he now? Etc. Still alive even, things like that. In the process of doing that, we discovered that this fellow was head in Soviet times of the Institute, at this time, of the Institute of Platinum. So many of you know platinum is an important material, rare material. It's important for all kinds of defense purposes and other purposes. So if you were head of an Institute of Platinum in Soviet Russia, you might imagine that you had certain connections. You weren't just an ordinary mineralogist. And he had those connections. He had aligned with the KGB and all that and the Communist Party. And he was known to be a not very nice person who put his competitors and got his competitors sent to Siberia and the like. Oops. Okay. So, but eventually I tracked him down and I discovered he had immigrated to Israel. So, on the internet, again, I'm looking at telephone books in Israel. I find someone with this name that's in outside Tel Aviv. I call him up, but no one at the house speaks English. So Hebrew to call up, and no one at the house speaks Hebrew either. So Russian's got to be the language of choice. Let's call him up, get someone who speaks Russian, who's going to be my Russian translator. And the guy comes to the phone, and first question I ask him, are you the Leonid Razin who, author of Razin, who's the author of this paper? I am academician Razin. Wants to be very formal. Okay, well, fine. Okay, but are you this person? Yes, I am. Okay. Are you the person who actually found this material, out of the ground? Because I wanted to know the conditions and where it was found and the conditions. And he said, yes. Great. Can you explain to me the conditions under which you found it? He began to give me a description, but that description was exactly the description that was in the original paper. Not a bit of information that I get from him that was not in the paper. Lots of questions to ask him. So then I asked him, well, do you have your geological notebook, which records that? I'm not sure. Maybe it's in Moscow. Now, I'd already been told and warned that, that's a super big red flag, because a geologist always knows where their geology notebook is. It's something that they sleep on. It's just always attached to them. It's just, they know exactly where it is. So if he doesn't know where it is, that's a really bad sign, a super red flag. Then I asked him, did he have more materials perhaps? He said, well, maybe, perhaps in Moscow. I said, by this time I had already checked the price. Moscow. I said, okay, I'm willing to fly you there, and I'll pay for a hotel, and can you check these things out? And that began a kind of peculiar discussion in which it took me several days to realize it, several back and forth to realize it, but he wanted a reward for this, a fairly significant reward for going to Moscow, recovering the notebook, and looking for more material. That was a real problem, because there was a certain chance that he could come back with a notebook, but no material. And if he did that, how could I know when that notebook was written? It could have been written like on the plane, on the way going. How am I supposed to know if all he's interested in is money, which seemed to be all he was interested in? So it was a tough decision, but eventually I abandoned that direction. It meant all connections now were set. No connections to any existing material on the planet. Then one of those miracles happened that was times in this story, but probably this is one of the really big ones, which is Lucas having dinner one evening with his sister and a friend, and telling him the story right up to the point that I've told you. And the friend stops him in the story when he mentions that there's this collector in Amsterdam. He says, what's the name of the collector in Amsterdam? I live in Amsterdam. So he tells him the name of the collector, and he says, that's too bad. That's a very common last name, like what we call Smith, and so you're not going to find this person. However, there is a woman who lives down the street. She has that last name. When I get back to Amsterdam, I will ask her. 24 hours later, an email arrives. Guess what? She's the widow of the collector. So, good news, we found the collector. Bad news, we're not going to be able to communicate with him, unfortunately. But the next day, we do send Luca to Amsterdam to talk to the widow and see what she knows. And she won't talk she's very suspicious of what's going on there. She won't talk to Luca, but she will talk to the friend. So Luca leaves, goes down the street to get coffee. The friend stays. Do you know anything about your husband's rock collection? No, nothing. It was his business, not my business. Do you know anything at all? Whom he used to do? No, I know nothing at all. I used to keep no track of it. I really know nothing, for about a half an hour of nothings. Until finally, I guess he wore her down, and she said, but my husband used to keep a secret diary, and where you record his. Although the collection went to Florence, we have the secret diary. So she goes to the diary, and sure enough, there's an entry there about this Katirkaiden having gone to Romania to. Somehow there was an exchange. It was illegal to do this in Soviet times. There was an exchange of something for something, at the end of which he had these minerals, okay? Money for minerals, illegal transaction, with a Romanian named Tim. So, Tim the Romanian is the next target that we have to go for. So when I got that news, I thought, wow, this has got to be easy compared to everything else we've had to do. How many mineral smugglers named Tim are going to exist in Romania? So 6 weeks later, no luck. Really worked pretty hard to do that. So now we're in trouble again. So as a last resort, this time we again send Luca to Amsterdam to talk to the widow. Maybe she's heard of this guy, Tim. And it's the same thing replayed again. No, she knows nothing about Tim the Romanian, knows nothing about the collection. She already gave up the secret diary. What do you want from her? Leave me alone. I've told you everything I know. Told you everything. No. I know nothing. Until finally, she says, okay, my husband used to keep a secret diary as well. For the dealings that were probably more questionable. And this is from the secret diary. Our guy, Tim, being mentioned. And it's mentioning that these minerals are coming from a certain laboratory, this laboratory of Rudashevsky. Ultimately, Rudashevsky is not just sort of like the material that Rosen, exactly the material Rosen collected. It obviously put part of it in the museum and smuggled part of it out through the sky chimney. Which is ironic because the way he'd get people sent to the Siberia was he'd accuse them of selling minerals to the West. He himself he knew he was selling to the West. So good news is now we know our sample has come from the exact same place as Rosen got his. Where did he really get his? By now we were sure he was not that kind of guy. He would never have dirtied his hands and gone off someplace to do it. So we were looking at all kinds of ways to try to figure out but we had been told by members of the Russian Academy of Sciences that hopeless, or we had given up on this guy for a long time. Suddenly, by accident, we ran across a paper in which he was the author. Which meant he was real, okay? Tell us how to find him, but there were other authors on the paper whom we could call, and by calling them, we eventually actually discovered that not only was he real, but he was still alive. And not only was he still alive, but we could get in contact with him. And within a few days, that's exactly what happened. Here he is, Valery Kryov, not on this particular expedition. Contacted him, of course, we were able to communicate by Google Translate. And he immediately began how he had been sent to Russia by Rosen to look. Digging in the stream, found some shiny grains. He knew they were afraid to go back empty-handed because he never did. So he brought him these grains to show that he had really worked hard and hadn't just hung out at this. That's the last he had heard. He did not know that Rosen had found new minerals, had published the new minerals, had smuggled it. He didn't know any of that story. But he knew one other thing. By now, the first announcement of our discovery had been made, and it got a lot of news in Russia because it came from Russia. And so he knew about that, and he got very excited about the idea. Map, exactly where he had found the material, which is one of the things we know. He also offered to help us. Meantime, we were working on this other line of reasoning. Could the rock have... By this time, we'd actually proven that it couldn't possibly come from a factory, because within those grains that are something that back to our original two theories. Turns out the way to test that is by measuring the ratio of different, depending upon where rocks come from in the solar system or outside the solar system. There's a kind of fingerprint test that you can do by tell you which it is. And you do that using a complicated back now, and we got a group there. It took a few months before the results came out, but when it came out, there was no question what the answer was. Forming probably, the ultra-high pressure would occur in a collision that occurs all the time in space between shock waves that produce the event. Contrary to what Glenn McPherson had told us, that he had seen every possible meteorite on the planet that had ever been gathered and that none had been found to have aluminum, suddenly this test left no doubt that the answer was there was a meteorite, and of course it did have aluminum. At the end of which, when he got this news, he immediately switched his opinion. 180 degrees. And then he put his arms around the problem. He said, "Now this is my world. This is I take over. I can tell you what to do next." And, no, thank you, Glenn. We'll work with you, but of course, by now, there were lots of questions we wanted to ask about this new material. A lot more tests to do, but all the sample had been used up getting to this point. The only way you could get more sample, the only hope for getting more sample, was to go back to the place where you originally found it. And that place is in this place, far eastern Russia, right across the Bering Strait. Possible to go there for a lot of reasons. It is a restricted region. Not even Russians can go there. That's partly for military reasons. It's part mining operations there, which are under tight control. That's impossible to do. Russian government, you need permission. Quasi, which is the FSB or the modern KGB. You would need local Chukotka government. You need, etc. Hope to get all that done in any reasonable way. You would need Valery, who's the only person who knows where to actually look exactly, to go with you. And he's now in his 60s. He was in his 30s before, but now he's in his 60s. You need members of the Russian Academy of Sciences to go with you. If you're an American, okay? You're going to need money. And try going to the National Science Foundation and tell them you're going to go on this wild, saw something a few decades. You have to get somebody who is have to get Luca, who doesn't do field work normally, to come out in the field with you, because he's the only one that saw the sample and studied it. Someone who knows something about structural geology, because maybe this idea of the meteorite's still wrong. Maybe there's something peculiar about the geology there, and someone who's an expert on that kind of issue for this region with you. It wouldn't help if he's also a bear expert, because there are bears in this territory. Nasty bears, Kamchatka brown bears, which if you don't know about, nasty as grizzly, nastier maybe than grizzly. Time, but a few hundred miles to the south. It actually wasn't attacked by grizzly bears. Meteorite expert, again, Glenn was not someone who works in the field. Translate for you, because the Russians speak Russian, we speak English. You need muscle to do all the digging, and muscle to a scientist means so. Mike Eddy, who was championship muscle. You're going to what? You're going to divers. Bogdan. You're going to need a cook. You need a lawyer to negotiate. You're going to need someone who has biology experience, who all those three properties are in Olya. that small team. And we're also going to need protection from very nice and friendly, but was pretty confident. No. Gave us a lot of self-confidence. If he was okay, if he was comfortable, I guess we should. There were lots of bear tracks around our never camping as a kid, never outdoors, never overnight. My first experience camping outdoors was there in the tundra of Kamchatka. And my teacher, who taught me how to survive, was Will, so which I think was good for lots of laughs that he'll remember. Had a lot to learn. Anyway, this is what it was like to travel out from Anadyr, the capital of Chukotka, out to the mountains, to the stream where the original material. I'll try to turn up the sound on this just so you can get an impression of it. You had to travel in these vehicles. And these vehicles, I was told, we were going there, were supposed to be these trucks. And I remember when they told me there were going to be trucks, I said, but I've been looking at Google Earth and I don't see any roads. And they said, oh, no, there's roads. Don't worry about that. That wasn't true. Don't worry about it. Traveling in one of these trucks. So every few hours or so, you're doing one of these. So these are like tanks on the bottom and funny vehicles on top. Now in this case, we were looking for a trail, but I didn't see any trail, so I turned to Victor and I said, Victor, where's the trail? And he gave me a funny look, as if to say, trail? Who needs a trail? And don't worry, the trees pop up afterwards and not killing anything. Part was crossing the Katirka River because this is permafrost territory. You have no idea what the depth of the river is. It changes from year to year. And we were told also that these trucks float. We were also told that it has never been tested yet when it was loaded down the way ours were. So, and you have to go both ways, by the way. You go, if you make it, you still have to go back. And all jokes aside, there were various disasters and threats along the way. That's a fire, breakdown, and other things that occurred. But we did manage to get there. There were nevertheless, actually got to the hill. We're back in 1979. Valeri, who's in the middle, Luca's on the left. Materials are embedded. This material is full of this very thick, gummy clay, which in a matter of hours destroyed all our shovels, except for a hand shovel. So the rest of the digging of a look at the, if you look in there, you might notice a little shiny something on there. That shiny something turns out to be a fragment of gold. So we did find gold. But you can't find a quasi-crystal by sight. You just basically have to do all this panning and collect as much material as you can and hope that you got something interesting, carry it back, and only check it back in the laboratory. Here we are on the last day of the that are about to leave the next day, and you might notice everyone's dressed a little bit more warmly than they were on the days before, and that's because fall has come to Chukotka, on August 3rd. August 4th, we leave, stay overnight, we look back the next morning, we look back where we came from, and winter has come to Chukotka. So we got there just in time that the soil was soft enough to dig in, and we got out just in time before the came to Chukotka in winter. Lucky, because we could have easily been trapped there. And another group that did try to go back a few years later did get rescued too. But so that was the end of the expedition. You come back, you have no idea what you've got. You just have a bunch of grains of material, millions of grains of material, and now you have to look at them one by one. And Luca is the world's expert for looking at them, and so he did most of the looking. And after about 6 weeks, he came back and reported, here's an interesting grain. This grain has this blackish material in it, which is very much like a meteorite. Furthermore, it has this shiny stuff on it. And when he took that shiny stuff off and he took the X-ray diffraction pattern of it, so this is now X-ray, he found this pattern. And that's exactly the pattern you expect to get for a quasi, just like the material we had. And when we measured the composition, it also had the same composition. So this was a really key moment, because the story I've told you, how we got to this point, you know the answer, but we didn't know the answer. We're all suspicious whether we put this. Now, this is a sample. We knew exactly where we picked it up out of the ground, exactly, buried in. Knew where it came from Chukotka. You bring it back, and we find the exact. This deck verified everything in one stroke that led to the acceptance of this material, natural quasi-crystal to be accepted. The name is icosahedrite, named after the symmetry of the. Could be the end, but no. We found eventually 9 samples in the material. We found among the material 5 new crystalline minerals, each of which is now named. And this is one which is my favorite, because this is one that Luca arranged to have named after me. It's called Steinhardite. So I've now been mineralized officially by this process. But it's a crystal. But then in searching for this crystal, we also found something else, which is this guy. This guy has a diffraction pattern which reminds me. Kind of quasi-crystal, a different, not that has this symmetry, stack of decagons. So it's another quasi-crystal number 2. Turns out this one had been formed in the laboratory. And this is a sample. It's become quite famous in the field, including in regions. Then a third thing, something we didn't expect. Another quasi-crystal, the third. Has different chemistry. So it's really something different. And unlike the first 2, which had been known before, this one was not known before. So this is the first example of a quasi-crystal discovered in nature first, before found by humans. And that was, to me, a key milestone, because that was part of the reason for looking in nature. Here's at least the first example. That's not the end of the story by any means, but it's the end of the lecture. So you'll be thankful for that. But I'm happy to answer any questions. Thank you for your attention. So we have one meteorite, which in which the quasi-crystals have been found, excuse me, in which the quasi-crystals have been found, yes. That's the only one that we've we've not done a systematic search through other quasi-crystals, through other meteorites at this point. We're thinking about ways to do that, but it's the only one known. So 3 different quasi-crystals from just one meteoritic event. Now, not just interested in looking now for quasi-crystals, just for quasi-crystals. Oh, thanks. We're also interested in looking to see if there's any metallic aluminum at all in any other meteorite other than this one sample. And up until recently, I would say the answer was no, but I think I can announce this today. There is a sample that's been recently recovered from the desert of Sudan, in which now they've all seen the second meteorite, which has aluminum copper alloy in it. So we now know it's also a meteorite, so we have a second meteorite which at least has the peculiar chemistry. We haven't yet seen a quasi-crystal in it. It may not have anyone in it because it's rather small, but the fact that it has the aluminum copper at all is an amazing thing, and is an important verification step in the process, and may motivate, now a lot more search through meteorites. Work my way this way. I'm going to start in the back first. Yes, yeah, with you. Good question. Okay, so this meteorite, not just any old meteorite, it's a very special class of meteorite. Interesting meteorite. When we were looking for this quasi-crystal, I was hoping to make something that was accidentally overshot, 4.5 billion years old. It has something to do with the formation of the solar system. A lot more interesting now. It's not just about quasi-crystals. Something that was there as the planets were forming and may be part of the cores of planets. That's why we're investigating. Oh, you mean like a spaceship or something like that? That's our favorite straw man theory, the alien spaceship theory, yes. Not likely, not likely. But the reason why we have that as our straw man theory is theory to qualify as being good, it has to beat that theory. It has to be more likely than that theory. So we have some ideas we think are more likely than that. And that's what some of the later tests have to do with. Other circumstances where you could. So one possibility, the leading idea is it was just a certain region of gas in the early solar nebula which had an unusual lack of oxygen. Not likely, but not so unlikely. Another possibility is it comes from outside the solar system. It came to our solar system. What happens to some of the materials? Those are the two major things we're well, you can read the book to find a little bit more about it, but it really begins when I was a kid. Okay, so I was interested in the issues of symmetry and mathematics and symmetry, shapes, the idea that this idea that there's these restrictions in what patterns you could make. It's just one of those things when I read it the first time just fascinated me, and well, as I described in the book, I was also reading, I also read at a point Kurt Vonnegut's book called Cat's Cradle. And if you know that book, in that book, there's an imaginary character who discovers an imaginary new form of water, which plays an important role in the story. Ice Nine is the name of it. I don't know the story. It doesn't have a happy ending. But as a scientist reading the story, it got me the idea, well, there could be forms of matter that people just haven't thought about before. Because we wait to see what we find in nature, or we wait to see what we find in the laboratory. And so, I think that idea was always in my mind, and then there's a longer history that gets me to quasi-crystals. But that's where the seeds of the idea came in. Sorry, he was first, then we'll work it. alloys in this case, yeah. Um, uh, yes. Yes. So because of the symmetries, not in the same way different, but they have other differences because the atoms are arranged in a way that's non-crystalline. So buckyballs are actually arranged in a crystalline array, but they have certain local bonds. This is different. This is the overall pattern is a difference. That's enough to produce differences in conductivity, elasticity, hardness, and things like that. And some of the early applications of quasi-crystals take it. Some of the work I'm doing these days is on studying, we make synthetic quasi-crystals, essentially 3D printing them, and then using them as a kind of way of channeling light, as if you again, taking advantage of their high degree of symmetry compared to ordinary crystals. Well, first of all, almost all of us were volunteers, and we had volunteer time. So, for example, to get use of the instruments, the director of the laboratory at Princeton, he has director's time, which gives him, free, he's allowed to use as he wishes. And he just donated that to us. Of course, I wasn't working on a grant either for this work. And the people who came on the trip just volunteered. They just thought it was such a to go to that part of Russia to do geology was a great opportunity for an American. You can't normally do it. They were eager to do it. Yeah, so fortunately, you just have to find people who are talented, and so the cost was actually not that much. You only had to pay. We had to pay trucks and airfare and things like that, but it wasn't that overwhelmingly expensive. It was like $150K for the entire. But the rest of the work was volunteer. Essentially, no grant money involved in it. I like the amount of science that came out for no grant money. You're next, yeah. And I'll go back here. Yeah, so it has aluminum, copper, and iron, but in a very different mix than the. I didn't spend time showing you the two images too closely, but if you look at the two images, you can really tell from their shape, the way they form, they have very different morphology. So that difference in chemistry is really a significant difference. One forms kind of nice little flowerlets, and the other one looks kind of. So Valeri, I mentioned that once we found this paper by Valeri, Kryachko, that he showed us that he was alive. It didn't tell us how to find him, but I could locate the co-authors. One of those co-authors, one of them was on the trip with us. And it turned out when we contacted him, it took me a while to get him, when I finally got him on the phone with a Russian translator, it turned out that at this point we didn't know Valeri was alive. It turned out he began by telling us that Valeri had been his PhD student, and they had done many projects together. Not this project. He met him after this trip. And both he and Valeri immediately suggested that we take a trip to Chukotka to look for more. They said, we'd be happy to help support you. So they just jumped to it. I just think they thought it was a neat thing. Oh, you mean how to get all the Russian authorities? Well, I have to give credit to Vadim Disler, the person I mentioned, and his supervisor, Marina Yudaskaya. They worked like crazy to do all the paperwork, which was literally a pile this high of paperwork, because it was all brought to Princeton, because we had to get things co-signed and things like that. And they did it with remarkable speed. So when we got these results back from Caltech, it was like October. Months before the next summer. They got all the work done by them, which anyone else would have told you would have taken about 5 years to go through. They just worked like crazy to make it work. We just very quickly formed a strong bond. I brought them to Princeton, so we had a chance to meet one another, to plan the trip, and there was just a really strong bonding that came from that. It was important because we were trusting them with our lives, including my son's life and my life, but my son's life in particular, I was interested in, as well as the others. And so we had to know that we could trust one another. That came immediately. They were just great people. They just worked it through, and probably there was a certain amount of bribing taking place for some of these funds, which I did not want to hear about. And I'm pretty sure that was going on as well, just to be able to get the material out of Russia. Back, and then you, yeah. No, and we think we understand why, because material on the surface of the moon gets heavily pelted by meteorites, which would probably melt and destroy the quasi-crystals that were there. That's our current idea, but we haven't given up on the idea. So we are going back to NASA to look at various materials that come from the moon, but from not the initial rocks, but because, well, we're also collecting material from satellite that collected cometary dust. So we're investigation continues. We want to know whether this, I mean, it'd be very important to know whether or not this material, the aluminum, copper, immediately formed within the solar system or outside the solar system. If it's outside the solar, either way implies some kind of new physical process. You want to know how common it is, because that'll tell you something about how relevant it is. Still hot on the trail. Okay? All those things and more. So one of the things that we did in the process of trying to understand whether it could have formed, just to give an example, I'll name one example, just to prove that it had something to do with meteorites and collisions and things like that, is that we actually, not up anymore. Okay. Can't show you. We actually used a device called essentially a cannon to reproduce collisions between materials to see if we could produce quasi-crystals that way. Smash them together like might happen in a meteorite sample, quasi-crystals that way. What we found is not only could we do it, it was really easy. In fact, it's one of the best methods I know of, maybe the best method for exploring and looking for new quasi-crystals. Not only did we make the ones we wanted, we made a bunch of others that by accident that we didn't expect to. So it's got us thinking, now gets us to applications, that this might be a way of quickly finding new quasi-crystal materials. And each one's going to have its own chemical and physical properties. And it might be a way of finding ones which are optimal for any given. That's just the tip of a large. So I think I should thank you again at this point for your wonderful